Hey guys, this is John. In today's video, we will be covering how to solve Laplace's equation on an annulus. This is the fourth video in a series about solving Laplace's equation on various types of surfaces. And I would say this annulus problem is one of the more, I would say it's like medium or medium to hard difficulty, but it's something that comes very frequently in harder versions of MATH-241. So I definitely think it's something worth looking at in the case that it does come out, because this specific question right here is actually from Mayo Taskevich's midterm 1 from spring 2019, and I've also seen another one of these annulus questions come up on a third midterm in another class in 2019 as well. So these type of problems are definitely, I would say they're not too bad, but if you're seeing it for the first time, it's definitely something to be very careful about. But let's get started on it. So we're told that we're supposed to find some function u of r theta that satisfies the Laplace equation inside a 90-degree sector of a circular annulus, okay? So step 0 on approaching these problems is to always draw the shape. Draw the shape and label, okay? So we're told we have a 90-degree sector of a circular annulus, okay, with inner radius 1 and the outer radius 4. So obviously this is not to scale in any way, shape, or form, but so inner radius of 1 and then outer radius of 4. And let's call this point the center, quote unquote, of the circle. Okay. And then the angle is from 0 to pi over 2. So you have any other boundary conditions? Okay. So we're also told that we have Newman boundary conditions, so first derivative boundary conditions at these various sides. Equals 0. And then similarly on the other side, theta of r pi over 2 is equal to 0. Okay? And then we're told that on the outer edge of this circle, u for theta, we're equal to 1 plus 255 cosine 2 theta. And on the inside, we're equal to u1 theta is equal to 0. And then, of course, we have a Laplacian u is equal to 0. Okay, so now that we've drawn and labeled our annulus here. Oh, so just in case you don't know what an annulus is this sort of thing right here. So sort of like a pendulum sort of module. Yeah, okay. So now step 1 is to separate variables. But thankfully, we're already given what the separation of variables is for. It is for this problem, right here. So we know that the Laplacian of u, right, del u squared, is equal to the thing above here. Just gonna copy it down here for notation's sake. R plus 1 over r squared, partial squared, u partial theta squared is equal to 0. Okay, so if we let u r theta be comprised of g of r and then phi of theta, we're given that this separation results in 1 over g times r times ddr r dg dr equal to negative 1 over phi d squared d phi d theta squared. Okay, and since we have all the variables separated successfully now the first step to this problem is to figure out the value of the separation constant. Okay, remember that when we're solving these types of problems, we want solutions where we have homogeneity when we have homogeneous boundary conditions. I'll write this out. When we have homogeneous BCs, we want oscillatory solutions. Okay? And if you've watched my previous circle video, we also noticed that when we have homogeneous BCs in theta, right, we want our solutions in theta to oscillate. So consequently, in order for them to oscillate, we want sine and cosines, and to get sine and cosines, we have to have imaginary exponentials. So consequently, to satisfy the right-hand side of this equation right here, which I'm going to circle with green, the solution for phi will result in sine and cosine functions. Okay? Cool, so we want our separation constant to be positive. So now, second step is to solve the diff EQs. Okay, so let's solve the right-hand side first. So for the case, so the general differential equation for phi is going to look like this, okay? But then we have cases to take a look at. So let's first take a look at the lambda greater than 0 case, because remember, lambda can be equal to 0, greater than 0, or less than 0. Okay, so for greater than 0, we have the solution of the differential equation, which is c1 sine square root lambda theta plus c2 cosine square root lambda theta. Okay, applying the boundary condition, we have to take the first derivative of this function, which gives us c1 square root lambda cosine square root lambda theta minus c2 square root lambda sine square root lambda theta. Okay. The first boundary condition tells us that at angle 0, we're equal to 0, and that this is telling us that c1 times square root lambda is equal to 0. But remember that square root lambda is non-zero. So therefore, c1 is equal to 0. Okay, so let's move along. So now we have to take a look at the other boundary condition, which is pi over 2. Okay, so evaluating this at pi over 2, because c1 is equal to 0, we can ignore the first term, but then we get negative c2 square root lambda sine square root lambda pi over 2, okay, is all equal to 0. Once again, we know that lambda is non-zero. However, if we set c2 as 0, then our function for phi would just be literally phi equals 0, right? And that doesn't really help us at all, because if phi of theta is just equal to 0, then that's just a trivial solution, and that doesn't really give us any meaning. So we're going to look for zeros somewhere else, and we can find these zeros in the sine function right here. So sine is equal to 0 for for a certain period of n pi. Okay, and consequently, sine is equal to 0 for when lambda, for each lambda where lambda is equal to 2n squared. Let's put this in green. And then our differential equation for phi is simply going to look like c2 cosine 2n theta. Cool. Okay, so chugging along now, we also have to look at the lambda equals 0 case. And then looking at the lambda equals 0 case, this tells us that our differential equation for theta is going to look like this. So c3 theta plus c4. And then if we evaluate the boundary conditions, right, eval BCs, we find that phi of theta for lambda equals 0 is just equal to a constant, right? So this means that lambda equals 0 is a possibility. So therefore, we must include it in our set of solutions. So consequently, this n right here has to be inclusive of the 0 case. So we can start from 0 here, n equals 0, 1, 2, blah, blah, blah. So lambda could be equal to 0, lambda could be equal to 2, lambda could be equal to 8, so on and so forth. Now, if we do the lambda less than 0 case, which I'm not going to write out explicitly, we find that there's a contradiction. When lambda is less than 0, we find that phi of theta is equal to 0, and that's trivial. And therefore, lambda cannot be less than 0. Okay, so we don't have to worry about the lambda less than 0 case. Okay, so now let's look at the other part of this differential equation. Let's look at the g part now, where g is a function of r. Okay, so once again we have to case through lambda greater than 0 and lambda equal to 0. So let's look at lambda greater than 0 first. So when lambda is greater than 0, we can multiply both sides by g to move g to the right hand side. Then we can expand the left hand side out. and then move this term right here to the left-hand side. And since this lambda is the same lambda as before, we can plug in the lambda we found from earlier in the phi section, so this specific value right here for lambda, and then plug it into our differential equation here. So when lambda is greater than 0, lambda is equal to the value 2n squared of g equals 0. And this equation right here should seem somewhat familiar. This is an example of a Cauchy-Euler diff EQ. So the solution for a Cauchy-Euler diff EQ is going to be, let's see which constant we have not used, C5. C5 r to the 2n plus C6 r to the negative 2n. Okay, so now we have to apply our boundary conditions, okay? However, please be very careful when writing your final solution here, because in the previous example problem I showed, we applied the boundedness condition, which considered the fact that at the center of this annulus right here, in polar coordinates, we have a singularity at the center of the circle, okay? However, when we're working with annuli, it's entirely different. There's no boundedness condition because we don't even contain the center of the circle, as evident here. No boundedness condition. And boundedness condition is a term that's derived from Haberman's book. He claims boundedness condition is like sort of boundedness is essentially what I'm talking about here. The center of the circle has a singularity at 0. Heat cannot be singular at 0. So therefore, we need to make sure that our solution for our heat equation does not blow up at 0. And this sort of logic was applied to eliminating the certain constant terms in the last video, but we can't do that here. We have to do something a little bit different. We have to apply instead the boundary conditions I'm highlighting in orange now. Okay, we have to apply these instead. Okay, so let's apply the first homogeneous one first. So we're told that at g of 1, okay, at 1, we're equal to 0. And this consequently tells us that C5 plus C6 is equal to 0. And therefore, C5 is equal to negative C6. So now let's take a look at the lambda equals 0 case, because we cannot forget that. When we solve the differential equation for lambda equals 0, in the previous video for the Laplacian in a circle, we find that our differential equation for g of r for lambda equals 0 is equal to natural log of r plus some constant term. Okay. Once again, when we apply this boundary condition, remember that we do not contain the center of the circle. So don't just automatically drop the natural log term. I've noticed a lot of students do this incidentally just out of force of habit, but in these annulus problems, you have to be very careful about what you're choosing to eliminate. So at g of 1, C7 natural log 1 plus C8 is equal to 0. This relationship right here between what we plugging this in tells us that C8 has to be equal to 0 because the natural log of 1 is 0. Okay? So therefore, our general solution for g of r is just C7 natural log of r, and that's it. I should probably box this in green. Okay, so now we have differential equation solutions for g and for phi. And now it's time to put everything together. In step 3, put everything together. Okay? So remember that we initially defined u of r theta to be g of r times phi of theta. Okay? G of r has different values for the cases for lambda greater than 0 and lambda equal to 0. When lambda is equal to 0 for the phi function, we just have a constant, and when lambda is greater than 0, phi is equal to cosine 2n theta. So we have to be very careful when putting our product solutions together because we have two different sets of lambda solutions going on here. So So let's write this out very slowly and be very careful. So let's first address the lambda equals 0 case first. When lambda equals 0, I'm going to height lambda equals 0 solutions in dark blue. When lambda is equal to 0, we have this and this. And we have to account for them appropriately in our solution. So I'm going to call each of these constants different terms. So I'm going to call the first constant term by itself in the phi solution just called A. And then I'm going to call C7 B. We have to account for all these solutions. So this is for lambda equal to 0. Okay. Now we're going to take care of the lambda greater than 0 terms. And that's when n is equal to 1 or greater. And this can be correlated to n equal to 0. Okay, so when n is equal to 1, we have to take an infinite superposition of them and take their their linear combination of all possible solutions. So I'm going to highlight the greater than 0 terms in light green. So when lambda is greater than 0, we have, that's pen. Greater than 0, we have this differential equation and then this differential equation. So our solution is going to be a little long. So we're first going to have, let's call it C of R2n times cosine 2n theta plus d r to the negative 2n cosine 2n theta. Okay? And remember that we found in this highlighted area right here that the coefficients attached to r to the 2n and then r to the negative 2n share this relationship. And that relationship carries down to the values for c and d as well. So in this problem right here, c is equal to negative d and vice versa. All I have done is redefine the coefficients attached to them. Okay, so now let's apply the boundary condition, the non-homogeneous boundary condition we were given. So this specific one right here. So this is telling us that the outer radius, u4 theta, is equal to 1 plus 255 cosine 2 theta. Okay? So this initial condition must be equal to the right-hand side. So a plus b natural log of 4 plus summation n equals 1 to infinity of c 4 raised to the 2n cosine 2n theta plus d r to the negative 4 times cosine 2n theta. Okay? So this constant term on the left-hand side, which I'm going to underline in orange, and these lambda equals 0 terms are closely related to one another. Okay? Similarly, these underlined green terms and these summation terms are similarly related to one another. Now the question that arises is how you find them. Yeah, well, that's not that bad. So let's tackle the green solutions first. So for when n is equal to 1, in orthogonality principle, we find that the coefficients are equal to 255 in some manner. So for when n equal 1, we have this specific relationship. Cosine 2 theta plus d 4 raised to the negative 2 times 1 cosine 2 theta. We can eliminate the cosine 2 thetas, and then we can further simplify. 255 is equal to 16c plus 1 over 16d. But remember that c is equal to negative d, so let's substitute that in as well. So 16c minus 1 over 16c. Okay. So now we have to figure out how to isolate c here. So this is just algebra 101 at this point. 16 squared. So let's convert this fraction to 16 squared. Is 256. Okay, and if we subtract 250 there, we get that. And wow, this is canceling out quite nicely. So 255 divided 255, la-di-da-la-da, and then we find that C is just simply equal to 16. Okay. Therefore, D is equal to negative 16. Cool, so we found two of our coefficients so far. Let's go on and find the values for when n is equal to 0. So it's important to realize that you should also check, sometimes check your boundary conditions on your general solution. So remember we found this as our general solution. The slight problem that arises is that for the n equals 0 case, or when lambda is equal to 0, remember how we found that the constant C8 was equal to 0? Well, the constant C8 is essentially the term, the coefficient A that we defined in our general solution here. So what we should do is prove explicitly that A is equal to 0 in our general solution, and that might help us along the way. So for the n equals 0 case, right, so if we look at our general solution for when n equals 0, okay, u1 theta equals 0. This is the boundary condition right here from earlier. This tells us that a plus natural log of 1b is equal to 0, and this term must be 0. So therefore, a is equal to 0. Okay? So now we can continue plugging along and coefficient matching our initial condition here. So for this constant coefficient, this constant term 1 right here, so for u4 theta, okay, actually, let's not say that. So this left-hand side of the equation right here is only equal to the right-hand side for, sorry, this constant term 1 is equal to the right-hand side when n equals 0. And the reason for this is that cosine of 0 is just going to be 1, and then the terms will cancel themselves out, because you have c minus d, c equals negative d, so then c minus c will just be 0. And then you can explicitly solve for the coefficient b. So when u4 theta equals 1, we're going to have that natural log of 4b. And therefore, b is going to be equal to 1 over the natural log of 4. Cool. So what basically another way to view this is that we basically coefficient matched, right? So we knew that these terms I'm highlighting in red are going to have to share some relationship with each other over here because they have a cosine term attached to them, whereas the terms I'm highlighting in this lime green, the 1, and then these terms are going to share a relationship with each other because they don't have a cosine attached to them. So consequently, our final solution, where we basically put everything back together, is that, yeah, we're doing this right now. Sorry, this is basically step 4 now, isn't it? Because we're finding the value of the coefficients. Yeah, okay, sorry, I forgot to write the step 4. Let's move this down a little bit and put that step 4 down. Find coefficients. And then we can put all these coefficients back together. And the reason why I'm introducing this step 5 now is because these coefficients are just nice whole numbers, so we can easily just put everything back in. So for a general UR of theta, right? So our final solution to this problem, something you would put on your exam, is going to be equal to wait, I just make sure I did something right. Yeah, okay, sorry. 1 over natural log of 4, so this is the coefficient b, times the natural log of r from earlier. There's no a term now, okay? There's no summation term because we have found specific cases where n is equal to 1 in our summation, right? So n equals 1 is the term from the summation, plus 16 r to the 2 for n equals 1, if you remember, cosine 2 theta plus, minus 16 raised to the r to the negative 2 times cosine 2 theta. And that should be about it. And that would be your final solution. And I'm just going to explicitly write this. This is your C. This is your D. These are your terms for n equals 1. And these are your terms for n equals 0. And this would be your final solution now. In box that in blue. And we are done. So, yeah. Please let me know if you have any questions, comments, or concerns in the comments.